Okay, take a look, please. I'd like to finish up going through maybe some questions on the test. And on the second test, there weren't any, it wasn't so clear cut. I mean, I think I'll just go through the problems and you tell me when we get to one that you want to go through. This is one I want to go through. I'm assuming people may have had some questions on this kind of thing. Okay, so let's talk about this now. If we want to find the vertical asymptotes, once again, remind us, where does a vertical asymptote exist for a value of x where what happens? 0 on the bottom, but not 0 on top. Good. Okay, so a unique 0 at the bottom. So what do we do in this case then? Suggestions? Probably turn tangent into sine over cosine right away. So we could write this as sine 2x over cosine 2x times sine 2x on the bottom. Okay. LS. Okay, algebraically I can cancel the signs. That's good. Okay. And so I'm left with 1 over cosine 2x. Those are going to be the places, wherever that equals 0, those will be the places where we get vertical asymptotes. Okay, but this brings us back to another important review topic. How do we solve a trig equation like this? So you can wrap your brain around that. What do we do there to solve for x? There's a couple steps. What do you think? Think about that for a second. What are you going to do? How do you solve for x? What do you think? What makes this harder than maybe some of the other problems that we've dealt with when we're solving for x? What's different about this? Where is the x? It's in the bottom, but there's something else going on there. It's inside the cosine function. Yeah, so we have a composition of functions there, and the x is inside the cosine. And so you can't just solve for x directly like you could if, let's just say, by contrast, if we had something like x squared minus 1 on the bottom. We could just set that equal to 0 and solve directly for x, right? But here we can't do that because the x is actually inside the cosine function. And so the zeros of the bottom are dependent on the behavior of the cosine function, right? So what you have to do when you're dealing with solving trig functions like this, first of all, is you have to find the conditions of the trig function that are to give you zeros, and then ask where x will produce those, if that makes sense. So in other words, you got to think of the 2x, that's an angle, right? Think of that like a theta. And you can literally, you could even write that variable substitution. You don't need to, but let's just call it theta in our minds at least. Where would cosine theta equal 0? If we look at the unit circle. At pi over 2. Okay, so there's a place. Where else? 3 pi over 2. Where else? Keep going, right? You could go 5 pi over 2, 7 pi over 2. We could go backwards, negative pi over 2, negative 3/2 pi, etc. Infinite number of answers, right? How could we say all of them? What do they all have in common? If I start to write that list. What are those? How would you describe those? Okay, something like that, yeah, something like that. It looks like the part that's the same in each case is that, isn't it? That's the same every time. And what's changing is what the pi over 2 is multiplied by, right? But what could we call that set of values? This negative 3, negative 1, 1, 3, 5. What is that? How would you describe that set of values? The odd integers, right? Okay, so we have to say, what we need to say here is the set of odd multiples of pi halves. Now this goes back, we had this discussion, how do we say an even number in general? If n represents the set of integers. But what would the set of even integers be? Multiply by 2. Okay, so if n is an integer, then 2n is even. And what would be odd? 2n minus 1, or for that matter, you take your pick. 2n plus or minus 1 would make any difference. We have to just stagger ourselves, either in front of or behind that even integers, right? Make sense? Okay, so then we know that what theta has to be. Theta has to be some odd multiple of pi halves. So how do we say that? Theta equals an odd multiple of pi halves. You told me this is how you say an odd integer. So how do I say an odd multiple of pi halves? Well, not 2n. It's got to be 2n, like 2n plus 1. Because that, to us, that says odd number, right? Times pi over 2. Okay, and usually you'd see that probably written more like this. I think usually you put the 2 on the bottom. It doesn't make any difference though, same thing. Okay, so that's theta, right? That's the angle. But the angle is written in terms of x. Because remember, and this sounds kind of goofy, but we've talked about this before, the cosine, we just feed the cosine angles. It doesn't care how you get the angles, it just gets angles, right? In this case, you get the angles by multiplying x by 2, but it doesn't even know that. You're just giving it angles and it spits out values, right? So instead of theta, we've actually got a 2x. Our goal is to solve for x though, right? This is ultimately, we've got a function of x, and we want to know the x values where we have vertical asymptotes. So what do? Divide by 2. Yeah, divide both sides by 2. And I get x equals 2n plus 1 pi over 4. And that represents the infinite set of values in our solution set, but it's where they are. Okay. Make sense? Okay. So once again, there's really 2 steps. You got to do the trig part. You got to go to the unit circle and ask, well, now where is my angle equal to, in this case, pi halves, or an odd multiple of pi halves. If it had been sine, it would have been 0, right? Or pi, or 2 pi, which would have been n pi. Right? But in this case, we had to do an odd multiple of pi halves. So that's the trig condition. Where is my angle going to have the right values on the laps of the unit circle, right? And then, instead of the angle, you plug in the expression in terms of x and solve for x. Okay? That make sense? Okay? All right. Moving on. Okay, so which, I guess none of those look exactly like that. Which one would it have been? Would have been A, wouldn't it? If we just distributed the pi over 2, I guess. Well, we had, let me see that. We had, oops, 2n plus 1 pi over 4. I guess if I just distribute the 1/4, right, then I get n pi over 2 plus pi over 4. Maybe pi over 4 out front. That's their answer. Okay, same thing though. They just simplify. Although really the simpler way we had. I don't know why they do that. Okay, moving on. I'll just go through these and you tell me when we get to one what you want to do. Pass? Pass or do you want to do it?
Can you just do it?
Sure, yeah. Okay.
No, that's fine. No problem. Let's take a look at this. Okay, I'll make this a little bigger. Okay, there's a graph of our function, right? First of all, they ask, does f of 0 exist? Yeah, and that's just saying, is the function defined at x equals 0? Sure, it is, right? My pen is on the paper at x equals 0. Does the limit of f of x as x approaches 0 exist?
Yeah.
It does, right? Ants from both sides anticipate stepping on the same spot. Okay, does the limit of f of x as x approaches 0 equal f of 0?
Yeah.
It does. So then, is the function continuous at x equals 0? Because those are our conditions for it, right? Remember what we said is the value of the limit has to equal the value of the function in order for us to not pick our pen off the paper. Now, where that would have been different is, what if there had, it's sometimes easier to see a non-example. What if that had been an open circle and we'd had maybe a dot right there? The limit still would have existed, but the limit would have been there, and the actual value of the function would have been there, and they wouldn't have agreed. Then it wouldn't have been continuous. Okay? All right. Keep going. What was that? Oh, that's right. Okay. Okay, what about one of these? Okay. Yay or nay? You tell me. Yeah. You tell me, yay or nay on that one. They give us this piecewise function, and they just want to know a couple things about it. Stare at it for a second. Anybody want to see that? Did I hear a yes?
Yes. Yes.
Okay, yes, all right. Is f defined at x equals 2?
Yeah.
It is. It is defined, and right there I'm pointing to the value of the function. You understand? Now, a way to think about that in terms of pen on paper is defined if I'm actually drawing ink at that x value, right? Is the function continuous at x equals 2? No, I had to pick my pen up, right? Okay. What number is that? Okay, how about this? That's a busy looking one, isn't it? Okay. So select the correct description of the continuity of the function at x equals negative 1.5. So negative 1.5 looks like it's right about there. So what do you think? Is it continuous? Non-removable? It's continuous. If I look at, right there, look at 1.5, I'm just walking along that part of the curve. The ant is, right? So continuous. Okay, what if it was on an open circle? Then it would have to be discontinuous. Now, okay, but what kind? Like, let's say it was at negative 2 instead. What kind of a discontinuity is that at negative 2? Removable. Good. How come? Yeah, I can fill it in by either moving or drawing a single point, right? What if it was at negative 1? Non-removable. And in this book, in the Math Excel book, they would remember what they'd call that? Jump discontinuity. Good. As opposed to an asymptote they'd call an infinite discontinuity. Okay? All right. Moving on. That one probably okay. Okay. How about this? Define, here's our function g of x. It says define g of 5 for the given function so that it's continuous at x equals 5. Okay, that's kind of a disguised version of a problem we already did, right? Let's look at this a couple different ways. Can everybody here and make that a little bigger? Okay, real quick, at your tables, just join these guys there. Okay. Talk about the continuity of that. Discuss, see if you can arrive at some good conclusions about the continuity of that function. Okay, I want some details. Okay.
No. Let's see. The yes. Yes.
No, Heather? Oh, that's right. I knew that. No Ezra, it looks like either. Okay, so what kind of conclusions have we arrived at here? What can you tell me about the continuity of this function? Oh, it's got a hole. It's got a hole where? At 5. Yeah, it does. It's got a hole at x equals 5. Now, how would you know? What would you do to show that? Okay, we could take a limit, I guess, and try to evaluate directly and get 0 over 0. We could also just factor this thing, right? We know we're going to get, we said asymptotes where we have unique zeros at the bottom. We get holes where we have shared zeros, right? So if we were to factor this, freeze it. Okay, so let's see, I can factor what out of the top? 4. Okay, what else could I factor? That leaves me with x squared minus 25, which factors into
X plus 5.
Okay, and on the bottom,
X plus 5.
okay, so then I get a shared 0 at x equals 5, so that means a hole at x equals 5, right?
Yep.
Now, what's happening at x equals negative 5? What if I have a 0 at the top but not the bottom? What's that tell us? If I were to evaluate this directly at x equals negative 5, I would get 0 on the top and some number on the bottom. What's that mean? 0, yeah. It's just a 0 of the function, isn't it? X-intercept, okay? So we know we have a hole there, okay, part 2. Part 2 is define g of 5. Now, what does that even mean? Define g of 5. Let's make sure we get this math speak all figured out. Once you get that, once you become fluent in mathematics speak, which is a little dry, it makes these problems a lot easier. What's that mean? There's a hole in our function at 5, right?
Yeah.
So, what's it mean to define g of 5? We want to fill the hole in. We're going to say, okay, well, we're gonna define a value of a function at g of 5. So essentially, what we're doing is creating a piecewise function, right? We've got this g of x. We'll make a new function, call it f of x. It equals g of x, right? Whenever x is not equal to 5, because g of x is undefined there, right? And then we need to know what is it going to be when x equals 5. And that's our job. That's what we mean by define function, right? What are we gonna fill in to make this continuous? Okay, I mean, you're right in a sense, yeah. We wanna know what the number is gonna be, because if we graph this thing, we've just got, you're right, but I'll have you just be a little more specific. If I graph this thing, it looks like those cancel, so it just looks like x plus 5, right? So it looks like, there's g of x, right? What value do we have to define for the function to fill it in? Well, whatever that missing y value is, right? So what is x plus 5 when x equals, whoops, hang on, we're supposed to be at 5 now, aren't we? Should be out here. My hole's in the wrong spot, hang on, I gotta fix this.
I was like, whoa.
Whoops. Supposed to be like this, isn't it? So if I go out here to 5, that's where. That's where my hole is, right? I need to know what the x value is that goes in there.
It's,
Now, how do we do that mathematically? We can kind of finesse our way through this, and we can look at it in terms of a graph, and you guys are powerful thinkers. You think about what you'd have to do there, but what's our mathematical tool that we've used a ton that would answer that question? If I want to fill in the hole in the function, what would the ant do? I mean, he's walking along this function in a fog. He doesn't even know that there's a hole there, right, until he steps into it, right? What's that sound like? What are we doing? Finding a limit, sure, right? We just want to we want to find the limit of the function and give the function that value to fill. Where's the ant think he's going to step, and then give the function that value to fill in the hole, right? So we would just take a limit, and we've already factored it. That's good. Right, and we can cancel algebraically all that stuff, and what do we get? 10. So 10 is the answer. That's what the limit tells us it needs to be. Okay. Good. Okay, now how would we won't do this one, but it's the same problem essentially. How would we do this? For this function, should I make that a little bigger? Okay, how's that? Find the point of discontinuity. Is the discontinuity removable or non-removable? So to find the point of discontinuity, we would probably just graph this thing, right? Well, actually, we wouldn't have to graph it. We could just see what's the limit of this top part. Here's the other approach we could take, right? We could say what's the limit of that part of the function as x approaches -2. In what case would it be continuous? That 2 minus x squared is the function f of x. Every place except at -2, right? So in what case would the function be continuous? If the limit of 2 minus x squared as x approaches -2 is? No? Right? Does that make sense? We've got this function. If we graph this thing, maybe you can see it easier. 2 minus x squared is just an upside down parabola hoisted up 2, right? So we've got, something like that, right? Not very good parabola, but you get the idea. So at x equals -2, which is, where's that going to be? Somewhere like right down here, let's say. So down there, we've got our hole in the function, right? And where the function is piecewise, it's defined, they gave it a value at x equals -2. If the value happens to fill in that hole, it's continuous. If it doesn't, it's discontinuous, right? How would we know? Well, take the limit, right? See what the ants are, that's what the limit tells us, is where the ants think they're gonna step. So ask the question, where do the ants anticipate stepping? And see, is it at 1? If it is, it's continuous. If not, it's discontinuous, right?
You see by graph.
What's that?
You see by graph.
Well, this is the graphing calculator part of the test, yeah. So you could just see by graphing. And you guys don't know how to do that on your calculators, right? Okay. Questions on how to do it in your calculators? Okay, well, let's look. Oops. Okay, so here's how you can do it on your calculators. If you go, this is pretty slick. Okay, so if you just graph, if I graph this top function, 2 minus x squared, and I want to know what the limit is, well, actually what the value of the function is. It won't tell me the limit, but it'll tell me what the value of the function is. I just go into y equals, put in 2 minus x squared, and let's just go, how about zoom 6 for zoom standard. Graphs it, and there's two ways to do this. I can either go use the menu and go second calc, and that takes me to the calculate menu for a graph. And that's a really important menu. There's a lot of calculus stuff on here that we'll get to soon. But there's a lot of non-calculus stuff that's important too. You can find minimums, minima, maxima, zeros, just x-intercepts, evaluate functions, finds intersections of curves, all kinds of good stuff. What we're looking for here is the value of the function. So I would choose 1, and then just type in -2, and it'll tell me, see, look, it puts the cursor right on that point, and it tells me the x and y coordinates is an ordered pair. So the ant anticipates stepping on a value of -2, not 1, and so this is discontinuous, right? There is a shortcut for that too that I'll show you. If you just go, if you have one thing graphed, can't even be a plot, if you have just one curve graphed, there's a trace shortcut. You can just push the trace button. This is the only thing trace is good for, otherwise it's terrible. But you push the trace button and type in an x value, and it'll evaluate the function there. So I can go trace -2, it does the same thing, just a little shorter, okay? So then we would say this is, what's our best answer? So A, the point of discontinuity is at x equals -2, obviously, right? That's where we had a hole. Which kind of discontinuity is it? A, B, C, or D? It'd be A, removable, because redefining the function at the point of discontinuity to be equal to -2, that was our limit, right? Would fix the problem. It would fill in the hole. Okay? All right, so... Wow. Okay, just a little different vocabulary. I'm gonna go quickly through this too. This is something that you don't really see in our textbook, but it shows up in the Math Excel book. But it's good vocabulary. This is something you'd be likely to see in a college class. Give a formula for the extended function that is continuous at the indicated point. Same problem we just did. That's all it's saying is, if I wanted to extend this function beyond f of x has a hole at x equals -4, I'd have to create a piecewise function that fills that in. I'm going to create an extended function that adds 1 point. Does that make sense? So we would just take the limit of the function as x approaches -4 to know what the extra value would be, though, that we define at x equals -4. That's all we're doing. Same problem we just did. Okay. And that's just more of the same. Okay, more of the same there. The only difference there is that the limit this time, how would we do that limit? When we want to see what value does the ant anticipate stepping on when x equals 1 to fill in the hole? We'd have to, say it again? We'd have to use the conjugate, the rationalization strategy, the rationalizing strategy, multiplied by conjugates, top and bottom. Good. You guys are getting good at this. I like this. Determine where it's continuous. Okay. What about this one? There's another one. So it says, for what value of a, slightly different here, for what value of a is the following function continuous at every x? You see that this is really just like the problem we just did also. It's almost the same thing, but this time it's a little bit disguised. We've got to figure out what's the value, what's the limit of this function as x approaches 16, right? And, well, here. Actually, this is just slightly different. Different enough that we probably better take a look at it. Am I going through too many of these?
No.
You stop me if I was, right? Okay. Okay, here's how we can look at this one. And you can do this, you could conceptualize this math in a lot of ways. But if you wanted to be rigorous, in order for this function to be continuous, don't the limits from the left and the limits from the right have to agree? Yeah. Does that make sense? So here, let's look at this top part. It's defined as x squared minus 192 when x is less than 16. So we're going to take a left-handed limit there. So the limit of f of x as x approaches 16 from the left would be the limit of that expression, right? Now that's just a direct evaluation kind, isn't it? That's easy. And that's just, if I plug 16 in, 256 minus 192 is what? 264? Okay, so we get 264, we get an answer for that one, right? That's good. On the other side, okay, now we have to approach our limit from the right. The limit of f of x as x approaches 16 from the right puts us in that domain, the red domain. And we get the limit of 2ax as x approaches 16 from the right. What's that equal to? 32a, exactly. Sometimes people have trouble with, or this is a little mystifying, that plus sign there. As I'm approaching 16 from the right, make sure you understand this, because this comes up a lot with people. If I'm approaching 16 from the right, but I can evaluate directly, does the right even matter? Yeah. I'm just approaching 16, right? This just tells me the direction from which I'm approaching it. But I don't have any problems taking that limit directly. When x approaches 16 from the right, it still approaches 16, and so I can just do direct substitution and get the answer, 32a. Does that make sense? Now, for this function to be continuous, that has to equal that, right? So I just have to set the value of a to make that true. That just amounts to solving a real simple equation. 32a equals 664, right? Make sense?
Yes.
Okay.
It's just 64.
Yeah.
Oh, whoops.
Take off
That makes
200.
more sense.
Oh, yeah, whoops, 64. 256 minus 192 is 64. Yeah, see that?
That's about it, yo.
There we
I was
go.
like, whoa.
Whoops.
I was like, hey, yo,
You gotta watch
me.
me. So what's
Are
a?
we?
Two. There we go.
Yeah,
Yeah.
I know you.
Thank you.
Yeah, oh yeah.
Okay.
Right, Clayton?
Okay, and then these right here. Find the limit of 2 over x minus 1 as x approaches 1 from the right. Okay, let's look at this. You know, I think one thing I probably should have done a little bit more with this is I probably, starting now we will, probably should have talked about, yeah, what's the calculus, but also how can you use your graphing calculator to get these answers, because that's important to know how to do also. So, okay, so first of all, remind us, it's been a little while since we talked about this. How do we deal with this one-sided limit? If I try to evaluate directly, I get a 0 on the bottom. And weeks ago, that meant no limit, but then we were able to move beyond that a little bit. We said we can be more specific than that. It is no limit, but what kind of no limit? If I take the limit of 2 over x minus 1 as x approaches 1 from the right, so that's numbers like what? 1 point something, right? What am I going to get on the bottom? Okay, I'm going to get something, actually, something slightly positive, isn't it? 1.0001 minus 1 gives me a slightly positive leftover, doesn't it? So I end up with 2 over 0 plus. Now I know that if I get a 0 on the bottom, remember how we dealt with this. We automatically know it's explosive, it's infinite. But the question is just what flavor of infinity, right? The sign rule here tells us positive over positive is positive, right? How could we see that on the curve? Yeah, if we were to graph this thing and kind of make the window comfortable, what we'd see as we approach from the right is we'd see the function climbing up like that, right? Exactly. Yeah. Exactly. Okay. All right. I think that's pretty much covers everything that we didn't cover on the other stuff. And if people have individual questions, we can certainly get to those also. What I want to leave us with today, I want to just show you, I didn't leave myself very much time at all, but I want to show you something kind of cool here. Let's take a look at, I'm probably not going to get all the way through this, but we'll just finish it up tomorrow in our short class. Okay, let's evaluate, let's go back to our limit definition of a derivative, and let's evaluate the derivative of a constant real quick. Okay, so first, so this, you gotta dredge this up, this is important. What did we say, how did we define f prime of x, our derivative, in terms of a limit? That was the limit of what? Remember this? This was that picture we drew? Where we're going to make the secant line into a tangent line. Remember that one?
It's the delta.
There we go. There we go. Good. Right. As
Triangle X.
delta x. Okay. We got it. Good.
Triangle X.
Okay, so now let's make this specific. We always start with that general statement of the derivative, and then we make it specific for our function. Well, ours is f of x equals c. If f of x equals c, what's f of x plus delta x?
C.
Good question, huh? What is it? It's just c. Absolutely. Think about this in terms of a graph, and always try to think of it in terms of a graph. That's good. If our function is f of x equals c or y equals c, what's that look like? The horizontal line, yeah. Right, it's just a horizontal line with the y-intercept of c, right? And so no matter where I go with this thing, it doesn't matter what value of x I plug in, I know the y value I'm getting back is always c, isn't it? Right? And so this is just equal to c minus c over delta x, right? And I need to write that as a limit. I did give myself a lot of room. Well, I fondly remember sometimes back in the day when I had boards all the way around the room, and I just start over here, and we just would kind of work our way around, and then I'm kind of limited. Leave myself enough room half the time. I'm not smart enough to figure that stuff out. So what's that equal then? What's that equal? Okay, it equals, if I evaluate this, I get on the top 0 and on the bottom, as delta x approaches 0. Okay, 0. So that looks like maybe it's undefined, right? But it's not. There's a difference between those zeros. One's approaching. One is exactly 0. Wouldn't you agree that c minus c is exactly 0?
Exactly 0.
The one on the bottom is really just a small number. Positive or negative, it's irrelevant, right? What is 0 divided by any number? 0. So our answer, see how that works? So the answer, say it again.
Why is delta x negative?
Because delta x is approaching 0, but in a limit it never actually gets there, right? So you could make it as small a number as you want. 0 divided by any number, regardless of how small, is still 0. And so does that fit our picture? What's derivative mean? Isn't that slope of the tangent line? Now a tangent line is kind of, a tangent line of a line is just the line itself, isn't it, right? So the slope of this curve, which is really a line, it's always a horizontal line. It's always 0, isn't it? Right? Yeah. And so we would have expected that. If I asked you the question before we even looked at the calculus, you would have told me, yeah, it's going to be 0, derivative 0, based on the shape. But we just showed it, okay? There's no way out. We're done at 48, aren't we?
Yeah.
Okay. Darn it. We're really going 3 minutes. Okay, tomorrow. This next one you're going to love. This is a cool proof. It's not a proofy proof.